Welcome to this explainer on the absolutely mind-bending reality of the quantum internet. Look, I know it sounds like something straight out of a sci-fi movie, or maybe some bizarre thought experiment locked away in a university physics department, but it's not. This is a very real technology, currently being funded by literally billions of dollars. We're talking about systems running in actual fiber optic cables right under our cities and beaming from satellites orbiting right above our heads. The ultimate prize at the end of this road? A global communication network secured entirely by the fundamental laws of physics.
Okay, let's lay out a quick mental map for our journey today. We'll start with 1, the quantum rulebook. Then 2, building unhackable networks. 3, overcoming the distance problem. 4, the quantum cybersecurity threat. And finally 5, the global quantum race.
All right, section 1, the quantum rulebook, covering the bizarre physics of the ultra small. Let's ground ourselves in the absolute foundation here, the most rigorously tested physical theory humanity has ever produced. To really grasp what's happening, you have to contrast our everyday classical digital world with the quantum world. The internet you are using right this second to watch this runs on classical bits. You can think of them precisely like a light switch. They are strictly either off or they're on, a 0 or a 1. But the quantum internet, it runs on qubits. And thanks to a wild property called superposition, a qubit can exist as a mixture of 0 and 1 simultaneously, right up until the exact moment you measure it. It's kind of like a spinning coin in the air, right? It's just a blur of possibilities until it finally lands. Now, superposition is cool, but it's not even the star of our show. The real magic lies in something called entanglement. And it's fascinating because Albert Einstein viscerally hated this concept. Back in 1935, he derisively called it spooky action at a distance because he simply could not accept that the universe was genuinely this strangely interconnected. Well, a landmark mathematical test in 1964 and a 2022 Nobel Prize completely proved him wrong. Nature genuinely is just that spooky.
So what does this entanglement actually mean for us? Basically, if you measure one entangled particle, you instantly know the state of its distant partner, even if that partner is all the way on the other side of the planet. Now, because the outcome of your measurement is inherently random, this connection doesn't actually allow you to send faster than light text messages. You can't force a deliberate message into pure randomness. But it does allow for something just as magical: the ability to establish a shared secret that is physically impossible for a third party to secretly intercept. And that unhackable security is guaranteed by a completely unbreakable mathematical law called the no-cloning theorem. In our normal digital world, copying information is super easy, right? Copy and paste. But in the quantum world, making an identical, independent copy of an unknown state is a literal mathematical impossibility. Merely trying to look at a quantum state immediately destroys its delicate superposition. So this gives us an entirely new, physically guaranteed form of security. Any eavesdropper trying to intercept the data will unavoidably leave behind unmistakable evidence that they tampered with it. Which brings us to section 2, building unhackable networks, and how physics actually protects our secrets. Let's look at how this translates from the whiteboard into the real commercial tech protecting networks right now. Here is exactly what that looks like in action, using something called the BB84 protocol for quantum key distribution. Let's say Alice sends entangled photons and Bob randomly measures them on the other end. Now, because of that no-cloning theorem we just talked about, if an eavesdropper, we'll call her Eve, tries to intercept those photons, she can't perfectly copy them. She is forced to guess their state, and guessing introduces massive, instantly detectable errors into the system. If Alice and Bob see that the error rate is too high, they just discard the key because they know for a fact someone is listening. Eavesdropping isn't just hard, it literally breaks the laws of physics, which is a pretty incredible alarm system. Moving right along to section 3, overcoming the distance problem and the brutal limits of optical fiber. Taking this global requires overcoming a massive engineering hurdle because we can't simply copy or amplify quantum information when it starts to fade. The crucial sticking point here is distance. At about 100 kilometers, so roughly 62 miles, in standard fiber optic cables, photon loss becomes absolutely catastrophic. Because we can't use traditional signal repeaters that copy data, the photons just get absorbed by the glass until there is practically nothing left. This exponential loss is, without a doubt, the single biggest bottleneck to building a global network today. So what's the fix?
Well, the proposed theoretical solution is called a quantum repeater. Instead of trying to fire one photon across a massive continent-sized distance, you break the journey into short, manageable segments. At each intermediate station, you perform a brilliant little trick called entanglement swapping. This links distant photons into a shared entangled state without them ever physically touching. It's incredibly elegant, but it requires impossibly precise quantum memory to hold on to those fragile states. Getting this to work reliably outside of a pristine lab environment, that remains a major cutting-edge research frontier. Because glass fiber is so lossy, researchers decided to just look up. Empty space doesn't absorb photons the way glass does. To completely bypass those fiber limits, China launched Messias in 2016, which was the world's first quantum communication satellite. It beamed entangled photons straight through the vacuum of space, totally rewriting the record books for distance, and enabling the very first intercontinental quantum-secured video call between China and Austria in 2017. After a decade of flawlessly proving this tech actually works, Messias poignantly retired, burning up in Earth's atmosphere in early 2026, leaving behind a legacy of fundamentally changing the global communication landscape. All right, Section 4, the quantum cybersecurity threat, or the ticking clock on classical encryption. We need to pivot to the existential threat driving this entire field. And ironically, it's a threat created by a different branch of this exact same science, quantum computers themselves. So almost all of our modern encryption relies on highly complex math that normal classical computers just cannot efficiently solve. But a powerful enough quantum computer running Shor's algorithm, it could shatter that math in a matter of hours. Which brings us to this incredibly chilling phrase, harvest now, decrypt later. This is an active, ongoing threat right now. Adversaries and state-sponsored intelligence agencies are actively stockpiling our currently encrypted internet traffic today. They are just patiently waiting for a future quantum computer to be built so they can retroactively unlock every long-term secret, every healthcare record, and every classified document we are transmitting right now. But it is not all doom and gloom. Fortunately, the defense is already here. It's called post-quantum cryptography, finalized by NIST in 2024. This uses entirely new quantum-resistant lattice-based mathematics to fend off things like Shor's algorithm. And the absolute best part about this, it doesn't require fragile, super-cooled quantum hardware. It runs on ordinary classical computers as a universal software update. Major tech giants like Apple, Google, and Cloudflare are already actively rolling this out globally to billions of users. Even with those updates, we are still racing against a very real ticking clock, perfectly summarized by Mosca's theorem. Think of it like a simple equation. You take the total time it takes to fully upgrade all your systems and add that to the time your data actually needs to remain completely secret. If that combined total is larger than the estimated time it will take for a capable quantum computer to arrive, you are already too late. And that is a genuinely scary thought, for sure, especially given some 2026 research showing that artificial intelligence might be actively accelerating the development of quantum algorithms, compressing our timeline even further. Finally, let's jump into Section 5, the global quantum race, and take a look at who is actually building this unhackable future. Let's survey the landscape of this massive infrastructure race. Billions of dollars are fueling what is rapidly becoming a genuinely global arms race. China is currently operating a staggering 12,000-kilometer dedicated quantum fiber network, serving their government and banking sectors. Over in the United States, we're seeing huge grassroots commercial pushes, like America's first industry-led quantum network in Chattanooga, Tennessee, and New York's massive Long Island testbed. Meanwhile, the European Union is busy executing a massive continent-spanning initiative, and hardware companies like IonQ are rapidly consolidating to claim their stake in the future of digital communications. But you know, a mature quantum internet is going to unlock mind-bending applications that go way, way beyond just sending secret text messages. It's going to allow us to network separate quantum processors together for just massive distributed computing power. It will enable something called blind quantum computing, where you can send a complex task to a remote server, and that server performs the math without ever physically being able to see the data you sent. And it's going to network hyper-precise quantum sensors to dramatically enhance global GPS and even help physicists hunt for dark matter. The applications are endless. So, the big question, when does this genuinely arrive for everyone? Well, leading physicists writing in 2026 warn that we are currently sitting at a transistor moment. Think back to the early, giant, bulky days of classical computing. We're there. We need extreme patience right now for material science, precise manufacturing, and system integration to really catch up. Serious industry analysts project that widespread, broadly accessible commercial deployment is realistically looking like the early 2030s.
Look, the fundamental physics is real, the laboratory milestones are completely proven, and the global infrastructure race is well underway. As we inevitably transition from mathematical encryption to security guaranteed by the universe itself, the only question that really remains is, are we actually ready to harness the full power of the quantum realm? Thank you so much for joining me on this explainer. Keep learning, stay focused, and I'll catch you on the next one.